Good afternoon, people. This is Kali, and this is Neutron Decay Cosmology Television. So, yeah, I was just thinking about this the other day, but I was going to compare a Klein bottle because I'm pretty sure that this is on a 2D slice of it, but Shirley's Surface, as I like to call it, after my mom, but Shirley's Surface, which is this like one single-sided surface, right? You'd be up here, right? And you come down, and then you're at the event horizon, and then you cross over, and there's this junction point right there, which is where the two membranes crisscross each other, sort of, which has to happen when you're doing two-dimensional and three-dimensional. And all of a sudden now you're an antimatter, but you're also matter because there's only one side. And then you come this way and that way. So one turn you'd be facing upwards, this, and then there's got to be some kind of inversion that happens here. Or there's something that happens there, right? And then, that's the event horizon. In a Klein bottle, this is the Klein version, neutron decay. So now you're a piece of hydrogen, because neutrons decay into hydrogen, eventually. Neutron decays into hydrogen. It decays into a proton. We've gone through this before. Proton, an electron, and an antineutrino. If you haven't watched my videos before, a neutron decays into a proton, an electron, and an antineutrino. What's the V button, right? Yeah, that. Okay, and the proton electron is hydrogen, monatomic hydrogen. So the whole premise of neutron decay cosmology is that when a neutron hits an event horizon, it gets transported through the membrane, which is the quantum flux, essentially, and then comes out. So basically it starts to cross the Einstein-Rosen bridge at the event horizon. And where's it going to come out? And my argument is, and you can check the math, but it only makes sense that this is the way it's going to work because math, that if you're going in at the highest energy pressure right here at the event horizon, right? This highest gravity, highest energy density, everything is the most intense right here, right? This is when you're crossing, or over here, but we'll call it here. When you're crossing this membrane, which is the rest of space-time, basically. This is where your perforation is. This is the event horizon, right? And the event horizon gets transported to the lowest energy density point. Because where are you going to get this extreme energy? Where else would you come out of? You're going to come out of black holes while you're going into black holes. There are no white holes. White holes are not a singular thing. It sort of goes from, this is a collective. There's like 1,000 neutrons, let's just say, a given second, 1,000 neutrons are crossing the event horizon. Really, this should be 1,000 points. And then those points will gather together. And then it'll expand. But this is the transport. So you come out, your hydrogen, you follow your path of gravity. Oh, event horizon, you get transported, but now you're on the other side of space, right? Like, let's say you start on the outside. Starting on the outside. We're staying on the outside-ish. There. But now, you're on the inside. And you come like this, and there's a little workaround here. You go like this, and now you're on the inside, but coming down to be neutron decay. But now you're on the outside again. Neutron decay, hydrogen flows, gets condensed because gravity, fall through event horizon, reemerge as antimatter, hydrogen, matter, antimatter, oscillating between the two. But this is a single-sided surface, so it sort of doesn't matter whether you're matter or antimatter. If you are matter, you are the opposite on the other side because it's only got one side. You don't really have a choice at this point. That's the thing about single-sided surfaces, and that's why this is just a simplified, this is like the minimal Klein bottle. But there is a weird inversion that goes here. Same here, because you have to go through this perforation right there. right? That's a cheat of a sort. And the cheat here is that all points intersect at one point there, which is the Janus point. I think it's exactly the same thing. It is time. It's the infinitesimal that you can't actually touch, and therefore you have to go around it. The locus point of all vectors. Yes. And that would be this section here, because it's sort of cheating. This is where you're inside of the universe. You've gone through the event horizon. Somehow this is a substrata thing through this design of typical Klein bottle. But this is a cheat to make it look as good as possible in three-dimensional space or two-dimensional space. This looks fine, but it's really hard to communicate the fact that this vector goes right through that way. That it's not deflected down, it goes straight through, and that goes straight through there in all three dimensions. Anyways, I just wanted to compare to the two and see that they're essentially exactly the same. Neutron decay, gravity makes it come apart. Neutron decay, expand, gets cooled. When a neutron decays, there's an expansion of 10 to the 45th. We're going from a point particle to a cubic meter. The temperature would go down exactly that amount. No wonder it's so cold out in space. 10 to the negative 45 temperature differential right there, like that. Certainly no heat out in space. And the components, a proton, electron, and antineutrino, can't absorb photons because they don't have an actual orbital to do such. All you could get is minor scattering, and that's a scattering of 1 proton per cubic meter, 1 electron per cubic meter. And antineutrinos don't even count. So my calculation for the transparency is 10 to the negative 31st barn, as they call them. Just looking up some data for individual particles and then exponentiating from the volume, because it's only 1 particle per cubic meter out in the deepest space, which is where the Einstein-Rosen bridge would want to go, because it's got the lowest energy. You don't have to work. You can just penetrate the quantum basement in a second. Anyways, sorry to make so long. Have a beautiful day.